All right, everybody, very good to see everybody here. Let's get the lecture started for this afternoon. Now, I'm sure if you can read, so the title of the lecture today, it is all about work and energy. And I think you may fairly say that's a bit of an ironic title for the last lecture on a Monday afternoon. But I think we'll see how we do. I'm sure everybody's going to be okay. Before we kick things off with the lecture today, I just wanted to say really well done, everybody, with the workshop last week. It's really fantastic to see everybody coming along to the workshop, helping each other out, thinking about the questions, really working through those questions there. So very well done, everybody, with the workshops there, especially with the challenge question last week. Who tried the challenge question last week? Okay, yeah, very good. So very well done if you gave the challenge question a go as well. Did anybody work out what the speed was for the challenge question? Did anybody get the speed? So if you're not sure about that, we can also go over the challenge question, if you like, in the drop-in session right after this lecture, okay? So the plan for today, we're going to be thinking about work and energy. So let's take a look. Let's see what we've got on the menu today. So the first thing and the main topic for today is we're going to be figuring out, well, what are work and energy in the physics sense of the word? Because these are a couple of words which are kind of very common. You know, we use them in everyday language, right? So you might say, I'm not feeling, I don't really have the energy today, or maybe some days, I'm feeling really energetic. And same thing with work. Maybe if you guys have a job, you've got to go to work. I'm always saying, we've got the workshops. So these are two terms that we use very commonly in everyday parlance. But of course, in physics, they have a very specific meaning. And really getting a quantitative understanding of what this meaning is, that's a big thing of what we're going to be focusing on today. So a couple of other things we're going to be focusing on today are some of the key principles of energy, so how energy behaves. And I'm sure this is going to come as no surprise. We're going to be thinking about the units of energy. We're also going to be thinking about the different forms that energy can take, and we're going to be having plenty of examples and applications of energy. And like I said a couple of times before, it's really understanding energy, which is such a key thing, why so many people have to understand energy, even if you're not studying physics directly. Whichever subject you're studying, maybe it's chemistry, engineering, biology, earth sciences, energy is such an important concept. And it's only really by understanding exactly what we mean by these physics terms that we can really say exactly what energy is, and not just talk about it in that kind of everyday terminology, when we're talking about, I don't really have the energy for this today. I always like to illustrate the slides, start off with a bit of a picture here. So I just love this picture. This is a launch of a Falcon 9 rocket. And I think it's such a visual, such a visceral example of energy in business. And actually in this one photo, there's lots of different types of energy going on. And over the next week or so, we're going to learn about all the different kinds of energy going on in that photo there. So I think it's a very dramatic photo, very cool, always cool to see a rocket launch there, and lots of different forms of energy all going on. Now, I think that photo is a great photo of energy in business. Before we get right down to figuring out exactly what we mean in energy and all the kind of stuff for today, I'd just like to share with you guys one more fantastic picture, which I think really shows energy in business here. So I have this photo, an absolutely beautiful photograph of the International Space Station in orbit, taken by the Space Shuttle. And there's a couple of things that I really like about this photo that I'd like to point out. So first of all, it's a very obvious, very dramatic, very visual example of energy here, because the biggest thing that you can see in this photo, well, after the planet Earth, it's these enormous solar panels which are providing the energy for the International Space Station. Now, we're actually going to be learning a bit more about solar panels over the next few weeks when you guys start the coursework. And I think you can't really get a better example of solar panels than the International Space Station. Of course, there's lots of other examples of energy at play here. The International Space Station, it's in motion, and there's all other kinds of examples of energy. So clearly there's lots of things we can point to in this picture and say, okay, look, there's some energy. But you can really, in a sense, do that with any photo, because energy, it's such a fundamental concept. So there's actually something else that I'd like to highlight with this picture of the International Space Station, which has some relevance for how we're going to be learning about energy today. Because the International Space Station, it was first launched, the first piece of it was launched in 1998. Obviously, they didn't launch the whole thing at once. And it actually took dozens of launches over more than a decade to assemble all those individual pieces of the International Space Station, to put the whole thing together in orbit. And without laboring the point, I think there's actually some parallels to how we're going to be understanding energy today, because over the past few weeks, we've been learning about lots of different physics concepts. We've been learning about scalars and vectors and units and forces and kinematics and acceleration and Newton's laws of motion, all these different concepts. And today, we're going to bring all of these concepts together, put the puzzle together, and use everything that we've been focusing on over the past few weeks to understand energy. And that's really why we've been working so hard trying to understand all of those pieces of the puzzle, so that we're ready to bring them all together today to understand energy. So I think there is a nice connection there with the International Space Station. You can't just launch something like the International Space Station all at once. It takes a long time to connect all of the pieces of the puzzle together. So that's all I'd like to say in the way of an intro. I think let's start with a question. Let's start by thinking about what is energy. So we often talk about energy in everyday language. Let's start with this question here. What do we really mean in physics when we're talking about energy? Now again, this is a bit of an interesting question, because all of these options are things that you can do with energy. But in physics, the definition of energy, it's the one of these which is the most general. So it's a bit of a tricky one, just an extra thing to think about there. All right, let's see what everybody thinks. What do we mean by energy in physics? Let's see what everybody gets. Okay, most people are going for C. Okay, so very well done, everybody who gave this question a go, because all four of these things are things that you can do if you have energy. If you have some energy, well, you can raise the temperature of something. Or if you have some energy, you can increase the velocity of something. So these are all things that you can do with energy. But I think, as most of you identified, the most general one of these is that if we have energy, we're able to do what we call in physics work. So the correct option there, option C. So very well done, everybody who gave that question a go. Now, you might say, okay, well, that's what energy is, but we've really just then moved on and now we're talking about work. So I think you might fairly say, well, that's all well and good knowing what energy is, but what do we mean by work? So let's try another question now. Let's see what we mean by work when we're talking about physics. So when we're talking about work in physics, we mean we have the ability to do something. So what is it that we have the ability to do when we're talking about work in physics? So again, this is a bit of an interesting one, because all four of these options are examples of work. These are all things you can do with work. But the physics definition, again, it's the most general example of work. Okay, let's take a look. Let's see which of these is what we mean by work when we're talking about physics. Let's see what everybody thinks. What do we get here? Okay, so some people going for C, nobody going for B and D. So option C there, that is actually a classic example in physics of doing some work. So it sounds a bit technical there. What do we mean raising a mass in a potential? All that means is if we have some mass and maybe we want to kind of move it away from planet Earth or something like that, we have to do work in order to do that. So that is an example of work. But in fact, all of these are examples. And again, the most general one, if we think about moving mass, what we're really doing is we're exerting a force, and then we're exerting a force through a distance. So the most general option, the correct answer for this one is option A, okay? So exerting a force through a distance. That's what we mean when we're talking about work in physics. That's the one of these which is the most general. So very well done, everybody who gave that one a go, especially if you got that work is the ability to exert a force through a distance. Now, one of the important things about energy, you might have heard the very important principle of energy that dictates what you can and can't do with energy. And this is really central whenever we are working with energy. So we have several different options there. This one might be a bit tricky to figure out if you haven't seen it before, but maybe ask the people around you. I'll get this question going. Let's see what everybody thinks for this one. Okay, very good to see all the responses coming in. Let's see which one of these is the law of conservation of energy. Let's see what everybody gets here. Okay, so most people going for option D there. So what does that say? So energy cannot be created or destroyed, only changed in form. So very well done, everybody who gave this question a go. I think you guys have got it. That's what we mean by the law of conservation of energy. And this is an essential point whenever we're dealing with any questions involving energy. So just to reiterate what this means, we can't make energy, we can't destroy energy. Every physical process, it's really fundamentally the process of turning energy from one form into another. So even if you think about something like a power station, they might say, okay, we're generating energy here. They're not actually generating energy. They're not creating energy out of nothing. What they're really doing is they're turning energy from one form into another. So maybe in the power station, they're taking in some fuel and they're burning the fuel and they're turning that fuel into electrical energy. So they're turning one form of energy into another form of energy. Or if you think about people, you can eat some food, you're taking in the chemical energy of the food, and then you have energy to go and, go for a run or something like that. So you're not creating the energy out of nothing. What you're really doing is you're converting one form of energy into another form of energy. So very well done, everybody who got that one. Okay, that's a really super important principle when we're thinking about energy. Correct answer there, I think we said option D. Now, I'm sure this stage is going to come as no surprise. Whenever we're thinking about a new concept, very important to think about the units of it. So let's think, what are the SI units for work and energy? I'll get this question going. Let's see what everybody thinks for the SI units. So just a reminder that if we put something in the square braces, that means it's the unit of the thing inside the square braces. Okay, very good. Good to see those responses coming in. Let's see which of these are the units for energy. What's everybody get here? Okay, most people going for option D. Now, does anybody know what option A is the units of? Any thoughts there? Power. Yeah, very good, very good. And what about option B? What's option B the units of? Any thoughts? Pressure. Very good, very good. Units of pressure. And option C, what is option C the units of? Temperature. Okay, very good. And then, of course, option D, what is option D the units of? Work and energy. Fantastic. Okay, that's the correct option. Okay, so units of energy and work, they are joules. So very well done, everybody who got that. Okay, now just one kind of specific point to mention there at the top. So I'm saying the units of work and energy. Now, getting a bit technical here, when we're talking about work and energy, we really mean that work is a form of energy. So there's lots of different forms that energy can take, and we say that work is one form of energy. It's such a special form of energy, though. Sometimes we kind of talk about it as if it's somewhat of its own thing, but it really is another form of energy. And because their work is a form of energy, it has the same units as energy. So whether we're talking about maybe, chemical energy or nuclear energy or work, they're all forms of energy, so they all have the same units. Okay, so joules, the SI unit for energy. So very well done, everybody who got that one. Now, do you guys remember a few weeks ago at the beginning of the semester, we were thinking about base units and derived units? Do you guys remember that? Okay, so joules, they're not one of our SI base units. They're a unit which is made out of combining those other base units to get joules. So for this question, let's think about how do we have to combine our base units to get the unit for energy. Now, this question is a bit tricky, but you guys don't have to guess with this one, and you certainly don't have to memorize it, because remember that work is force times distance. And we saw last week force is mass times acceleration. So from those two pieces of the puzzle, we can put everything together and figure out what the units of energy have to be. So think about the units of acceleration, think what units that's going to give us for force, and then think of what units that's going to give us for work. So you don't need to guess with this one, and you don't need to memorize anything. You can figure it all out from the pieces of the puzzle that we have there. Okay, let's see what everybody thinks for the units of energy in terms of our SI base units. Let's see what everybody gets. Okay, so nobody's going for D. Kind of split between B and C. Some people may be thinking A. Maybe it'd be useful to kind of put some stuff up on the board here. Okay, so what are the units of acceleration? What's the units of acceleration? Meters per second squared. Very good, very good. Okay, so units of acceleration are meters per second squared. Okay, very good. So force is mass times acceleration. So what does that mean our units of force are going to be? Any thoughts? Very good, very good. Okay, so acceleration is meters per second squared, and force is mass times acceleration. So our units for force, it's just going to be kilograms times the units for acceleration. So kilograms, meters per second squared. Very good. Okay, so those are the units for force. So we're nearly there. We're making good progress. So work is force times distance. So what does that mean our units of work are going to be? Any thoughts there? Very good, very good. Does everybody hear that? So our units of work, they're going to be the units of force times an extra meters there. So we're going to have kilograms. So we've only got meters there, so then that's going to be meters squared per second squared. So very good. Thank you guys for helping me out with that one. So which option is that on the thing? Option C there. That's the correct option for joules in terms of our SI base unit. So very well done, everybody who gave that question a go. So if you'd like to go over any of this stuff, remember, we can go over this at the drop-in help session right after the lecture if you have any questions about that. Can anybody recognize what are the what's option A the units of? Anybody recognize that? Momentum. Very good, very good. Okay, and what about option D? Can anybody spot what is option D the units of? Sorry, which one? Newtons. So newtons are option B. Option B. You're thinking on the right lines. So what? D.
Oh, sorry.
Okay, okay. Okay, oh, that's fine, that's fine. Power, oh, very good, it's power, okay? So we're going to be learning about that very soon. So very well done for recognizing that that's power, okay? Because we've got that coming up, okay? So very well done, all of you guys. So we've covered some of the basics of energy. So we now know what is energy. It's a form. So energy is the ability to do work, and work is the ability to exert a force through a distance. And we know that energy is always conserved, so we can have different kinds of energy, but they're just flowing from one kind to another. And now we've done the units of energy, so joules, and in terms of our SI base units. So what I'd like to think about now is a very important form of energy, and it's the energy we need whenever we're moving anything against gravity. Has anybody done this before? How many people have done this before? Okay, a few people, okay, but not too many. Okay, that's really useful to know. So let's have a think about this. Whenever we are dealing with gravity, one of the fundamental things we need to think about is what is the force of gravity. So with this question here, suppose we have some mass, so it could be the little clicker here, or the remote, or any other kind of mass. What can we say about the force of gravity acting on the mass? So if you're not sure about this one, remember that force is equal to mass times acceleration. Okay, let's see what everybody thinks for this one. What's our force of gravity? Okay, so most people going for D, but not everybody. So again, if you're not sure with this one, you don't need to guess. It's not one of those ones where you just need to take your best guess, because remember, what have we got here? Force, it's equal to mass times acceleration. And if we're thinking about gravity, our acceleration is that little g there. So the force of gravity, it's just option D there. So it looks like most people got that one. Okay, so very well done, everybody who gave that one a go. So what we're thinking about is, suppose we've got some mass and there's some force of gravity, and we want to move our objects against the force of gravity, okay? That's the situation we're thinking about. So we've got some mass and we want to raise it up to a height. We're calling the height little h. Now, we've got a force, we've got a distance. So what this allows us to do is think about how much work we're going to be doing. So with this question, put the pieces together, figure out how much work do we need to do to raise our mass by a certain height. Okay, very good. Let's see how much work we've done to raise our mass. What's everybody got? Oh, okay, so almost everybody going for B. Okay, so very well done if you gave this question a go. Okay, so remember, in this situation, our force is mass times the acceleration due to gravity. Work is a force times a distance, and our distance is h. So our work is mass times acceleration due to gravity times h. That's how much work we're doing. So that's option B there. So very well done, everybody who gave this question a go, and especially if you got option B there. Okay, that's how much work we're doing. Okay. Now remember that energy, it's always, as we say, conserved. It's not created or destroyed. So we've gone and done this much work. Maybe we've done the work ourselves. Maybe we're weightlifting. The energy has come from the food we've eaten. That's given us the energy to lift the weights. Or maybe it's a machine like a crane winching some mass up by a certain height. So we've done some work. So the question is, now that we've done some work, where's the energy gone? Okay, so once we've raised our mass to a certain height, what's happened to that energy? What's happened to the work that we've put into the mass? With this one, I've just put the most commonly used symbols for each of these forms of energy. You might see some different symbols used for these ones, but these are kind of the most commonly used symbols. For potential energy, you might see U's or V's kind of equally as often. Okay, let's see what everybody thinks of this one. Where has our energy gone? What are the results here? Okay, so nobody's going for D. That's enough work. We've done some more work there. So now I can see why people might be going for option A, gone into some motion, because very often, you know, you do some work on something, maybe you give something a push and then it has some motion and it keeps on going. And we're actually very soon going to see an example of this. That's a very important kind of energy to think about. And also I can see why people might be going for option C, heat, because as we're going to see very soon, almost always when we're thinking about energy, once something's finished, the energy ends up just as heat. So in almost every kind of physical process that we might have, so, you know, our cells or a machine, you put some fuel in, so maybe you eat something or you put some, you know, some petrol into a machine and it does some work, it does whatever it wants, and then what you're left over with is just some heat. So I can see why people might be thinking it's heat, okay. But in this situation, we're thinking about raising a mass and we're not kind of giving it a push. It's not going anywhere, it's just stationary. And we're having a bit of a kind of idealized example where we can just raise something up and there's not any waste heat here. So where the energy actually goes is option B here. It goes into the potential energy, as we say. So correct option, option B there. Okay, so very well done with this question. And that's really what we mean by potential energy in physics. What potential energy is we have the ability to do work because of where we are. So if we think about raising our mass by some height h, it's now up on a nice height and it could now go and do some work. If you imagine maybe it's like a ball and then you push the ball off a hill, it's going to roll down and it's going to be able to do some work because of where it is, because previously someone's come along and done the work of pushing it up to the top of the hill. So that's what we mean by potential energy. Does anybody have any questions about this at this point? Let's just try one slightly more quantitative example when we think about exactly how much work we can do with a certain amount of energy. So let's think about this situation here. Suppose we have 1 joule of energy. For now, let's not worry where our joule of energy is coming from. And suppose we're trying to raise a mass by a height of 1 meter. So I guess this stick is about a height of 1 meter. So the question is, if we want to raise a mass by a height of 1 meter, and we only have 1 joule of energy, how much mass can we bring up to the top of that 1 meter? Okay, let's see what everybody thinks for this one, okay. How much mass can we raise by a height of 1 meter? All right, here we go. Let's see how much mass we can get. Okay, so not so many people going for option D. Okay, now this is a bit of a tricky one because whenever we're thinking about SI units, often everything comes out, you know, it's exactly, you know, 1 meter or, you know, 1 second or that kind of thing. So if we're thinking about we have 1 meter of height and 1 joule of energy, I can see why people might be thinking, okay, well, it's going to be 1 kilogram of mass, okay, because very often that's how things go with SI units. But we've got to be a bit more careful here because remember, so our energy, it's mgh. And if you just want to get a rough ballpark there, that little g, the acceleration due to gravity, it's basically 10 meters per second squared. So I can see why people might be going for 1 kilogram, but we've got to be a bit more careful. Now I can see why that might take you on to thinking about maybe we can then lift 10 kilograms by 1 meter with our 1 joule of energy. So a bit more mass, but we've got to be a bit more careful with the algebra there because what we're really thinking about is how far can we lift if we essentially have 1 Newton of weight there. So if we only have 1 Newton of weight, then we can only have that 0.1 kilograms of mass. Okay, so very well done everybody who got that one, the 0.1 kilograms of mass. Okay, that's the correct option there. So in a sense, that's what we mean by 1 joule of energy. So if we think about something that maybe weighs about 100 grams, so I don't know, maybe the remote's a bit light, but going to be fairly close. So if we're thinking about something which has a mass of 100 grams, and then we raise it by 1 meter, there we go, that is 1 joule of energy. That's what we mean exactly by 1 joule of energy. So we've talked a bit about different forms of energy. Energy can take lots of different forms and flows from one form to another. So what I'd like to think about now, which of these four it's not a form of energy? We're going to be learning about all the different forms of energy. See if you can spot which of these is the odd one out. Okay, let's see what everybody thinks for this one. Which of these is the odd one out? Which is not a form of energy? What does everybody think? Okay, so some people go for all of them. So very important to emphasize, so work is definitely a form of energy. In a sense, it's the kind of fundamental form of energy. Whichever other kind of energy we're looking at some level, fundamentally what's going on is some work. So some force is being exerted over some distance. Now, heat, we haven't directly covered heat yet, but over the next couple of weeks, we're going to be focusing a lot on heat and heat energy. So heat, very important form of energy. So we're thinking about B and C. Now, quite a lot of people going for mass, not so many people going for force. So between the two, we can tell that force, it's not a form of energy. Really, if we're thinking about, work, it's force times a distance. So if we have to multiply something by a distance to get a form of energy, then we know it's not a form of energy. So looks like most people going for option B, so mass. Oh no, we're going for which one is not a form of energy. Okay, so we're going for which one not a form of energy. Okay, so the one that's not a form of energy is force. Okay, so surprisingly, mass actually is a form of energy. Okay, force is the one that's not a form of energy. Okay, so which one is not a form of energy? Okay, so mass is actually another form of energy. I'm sorry I got that a bit muddled, a bit back to front there. Okay, so very well done everybody who gave that a question to go. Now, why do we think that? Why does it sound a bit crazy? Mass being a form of energy. What does everybody think about this one? E equals mc squared. Exactly right. Okay. Did everybody hear that? So perhaps the most important equation in physics, E equals mc squared. So Einstein's famous equation tells us that if you take mass and you multiply it by the speed of light, then you're going to get energy. Now, you might fairly say, well, hang on, this is supposed to be intro physics. I wasn't expecting too much, relativity and Einstein on kind of lecture 9. But what's great about this, and one of the reasons that I like units so much, is that by thinking about the units of this, that can really help us to figure out what's going on here. So, of course, the famous equation, E equals mc squared, okay? Now, it might not be obvious that that equation is telling us that mass is another form of energy, but let's take a look at the units. So I've got this question here for a few different options for what are the units of this side of the equation? What are the units of mc squared? So see what you think for this one. Let's see what everybody gets for the units. Now, again with this one, you don't need to guess with this one. We can tell from what goes into the equation what has to come out. So we know that m is a mass. Think about what the units of the mass are. And we know that c is the speed of light. So think about what the units of the speed of light are, and then think about what the units of mc squared are going to give us. All right, let's see what everybody gets for this one. What are the units of mc squared? What does everybody reckon? Okay, so we kind of got a lot of things, the bases covered here. Now, they all have kilograms to start off with. That's what we get from the mass there. That's giving us the kilograms. So really what we have to focus on is what are the units of c squared. So let's start by thinking about, well, what are just the units of c, what are the units of the speed of light? What is that going to be? Oh, yeah?
Meters per second.
Exactly, very good, meters per second. So the units of c are meters per second. So if the units for c are meters per second, we can just do a bit of algebra, work out what the units of c squared are. That's going to be meters squared per second squared. So when we put that together with the kilograms, what do we get there? Meters squared per second squared is option D. So that's what most people went for. So the correct option there. So very well done, everybody who gave that question a go. Okay, so the units of mc squared are kilograms meters squared per second squared. Now, does anybody recognize where we saw those combinations of base units before? Does anybody recognize that? It's joules, exactly right, very well done. So that combination of units, those are the SI base units for joules, the units of energy. Now, like I said before, you might say, okay, well, I wasn't expecting Einstein and mc squared and all of that stuff. And it's a bit more work to see, where does this equation come from? But one of the reasons that I like units so much, and units are so important, is just by thinking about the units of something, we can say, well, what if we took mass and we multiplied it by the speed of light squared? It's very curious that that happens to give us the units for energy. So even if you haven't studied relativity and worked through all the stuff that you need to get through E equals mc squared, by thinking about the units, that tells us, well, hey, that's kind of suspicious that mc squared, the units of that are joules. So it's a great approach. If we're thinking about the units, it can often give you very important insights there. And that's what gives us this conclusion that, in fact, mass is another form of energy, a very concentrated form of energy. And if we multiply mass by c squared, well, c is a big number, so c squared is a huge number. So it's a very concentrated form of energy. Now, next semester in further physics, we're actually going to be using this equation quite a lot when we're thinking about nuclear physics. So we're going to be working with it a bit more. But for now, I think if we're starting by thinking about the units, that's a great place to be starting with, okay? So I think that's a great place to wrap things up for the time being. Very well done today with all the questions. Okay, I know there are a lot of questions today, but people did really well in them, okay? So if you have anything you want to ask, we have the drop-in help session right now. Otherwise, I'll see everybody on Thursday. So I'll see you then.